Okay, 7.4 is on area and arc length. Okay, area and arc length. Okay, in polar, uh, and then we'll in polar coordinates, and then we'll put in parentheses parametric. Okay, because um, we're going to talk about the differences between polar and parametric at the end. Okay. Okay, so let's talk about a sector area. That's a piece of a piece of a circle. Okay, so the area of a sector is 1/2 theta times r squared. Okay, where r is the radius of the circle. Okay, and theta is the angle in radians. Okay, in radians. The default for angles is radians anyway, but I just want to make sure it's stated that. Okay, that's the area of a sector, of kind of like this cheese wedge. Okay, that's the area of a piece of a circle. Okay, so the area in polar coordinates, the area of a curve in polar coordinates, very similar. Okay, is approximately the sum of all these cheese wedges. Okay, it's the sum as I equals 1 to n. Okay, as n, and we're going to let n go to infinity and take a limit to get an integral. Okay, of 1/2 of, we'll call theta, or call r, the radius here, f of theta. Okay, so r is now a function in polar coordinates. Okay, r is equal to, say, f of theta, some function of theta gives me r, the radius. Okay, and then I square that, and then we just take a d theta or a delta theta. Okay, so if I had a curve, if I had some sort of curve and I want to find the area of some curve, okay, what would be the area of this curve? I would get all of these radii that would go out, all of these different r's, which is f of theta. Okay, and then we would get these cheese wedges, and we would find the area of all these little cheese wedges. And the higher the value of n, the higher the value of n, the more accurate we get. Okay, so if we slice this up into you know uh, 10 different wedges, that's going to be not as accurate as if I sliced it into 70 different slices. Okay, but each of them is going to give me the area, say, of one sector. Okay. So if I took, say, this guy here, okay, as one sector, okay, that's one piece of, okay, that's one piece of the total area. Okay, and the arc could be, anything. It could look like this. Okay, but we're still going to use polar coordinates to get all of our values here. Okay, and so we still end up with a bunch of slices, okay? We still end up with this kind of sector area. It's approximate, it approximates it, but when we take a limit, it actually becomes, okay, the actual area. So the integral from alpha, okay, to beta, okay, of 1/2 f of theta squared d theta, okay, is equal to alpha to beta of, okay, I'll just rename this r of theta, because that's how we see our polar equations in terms of r of theta, some r equals some function of theta, okay, and then d theta. So this is going to be our area formula, okay? So area is equal to this guy here. Okay, so let's do an example with this. Okay, let's find the area okay, of sorry, I should say enclosed by one leaf or one loop. We'll call this one leaf of the four-leafed, I don't know if it's leaved. I think it's four-leaved. Okay, rows. R equals cosine 2 theta. What does R equal cosine 2 theta look like? Well, okay, if I were to write out some values here, theta and then 2 theta and then cosine 2 theta, okay, and then R and theta. Let's write out some values here for this. Okay, I noticed that I'm going to skip a couple of lines here, and there's a reason for that. But I noticed that if I take 0 and I multiply by 2, I get 0. Take the cosine of that, I get 1. So this is 1 comma 0. Okay, at 0. That's kind of normal for a circle. Okay, but this is not going to make a circle. Okay, so that's at 0, 1 or 1, 0. Okay, what happens if I take, say, pi over 8? Then I get pi over 4, which is radical 2 over 2. So this becomes radical 2 over 2, pi over 8. Okay. If I take pi over 4, I get pi over 2, which is cosine pi over 2, that's 0. Okay, and so this be 0 pi over 4. Okay, so that's interesting. Okay, what does that mean? That we're at 0 pi over, well, let's write a couple more. Okay. So if we go to, say, 3 pi over 8, this becomes 3 pi over 4. The cosine of 3 pi over 4, that's in the second quadrant, so I know cosines are negative. This is radical 2 over 2. A negative radical 2 over 2, and 3 pi over 8. Okay. And then if I do 4 pi over 8, well, that's just pi over 2. If I multiply pi over 2 times 2, I get pi. The cosine of pi is negative 1. So I get negative 1 pi over 2. Okay, so let's kind of start there and see what's happening. Okay, so what is happening with my values here? So at 1, I'm at 0. At radical 2 over 2, that's the radius. It's 0.707. I'm at pi over 8. Okay, so to get pi over 8, I'm going to take pi over 4, which is the 45 degrees, and then I'm going to cut it in half. That's going to give me pi over 8. Okay? And this is of length 1. So 0.707, if I were to kind of do an arc here, that would give me length 1 there. 0.707 is going to be 7/10 of the way. 7/10 of the way there. And then I go to 0 at pi over 4. At pi over 4, I'm along this line pi over 4, but I'm now at 0. Okay, and so what's happening is I'm getting this curve that looks like this. Oops, I don't like it that it erases automatically. Okay, so I get this curve. Okay, so now what happens next? Well, what happens next is at 3 pi over, 3 pi over 8. Where's 3 pi over 8? Well, that's here. 3 pi over 8 is here. Okay, I go negative. I go negative. Okay, let's extend that to the negative direction. And again, if this is 1, okay, 1 unit, then 0.7 or 7/10 of a unit would be here. And so we actually go from here to here. Okay, and what happens as I continue this along, I actually end up drawing out the following figure. Okay, and it's called a 4-leaf rose. Okay, a 4-leaf rose. Okay, what I'd like to do, I should actually go there, but whatever. Okay, if we continue this from zero to 2 pi, it would. Now what I'd like to do, I just want to get one of these. Okay, so I have to choose how to get one of them, and I've got to choose, you know, the area, okay, maybe in just one of these. Well, the problem is that I started off at 0. I started off here. I started off right there, and it gave me the top half of this petal, the leaf of this rose. Okay, so it gave me the top half. How would I get the bottom half? Okay, so the top half of the petal, or of the leaf, I should say, is from 0 to pi over 4. Well, if I go in the opposite direction, if I go negative pi over 4, so this would be negative pi over 8, negative pi over 4, I should get the bottom half here. Okay, this bottom half will give me from 0 to negative pi over 4. It was the very last thing that I drew, but if I go negative, I can draw that piece. Okay, because at negative pi over 4, for my angle, this becomes negative pi over 2, which becomes 0. Okay, and so this becomes negative pi over 4, or sorry, 0, negative pi over 4. So it goes back to 0. Negative, sorry, it should be 0, negative pi over 4. Okay, if I did negative pi over 8, that should give me this point here. Let's see if it does. Okay, does it give me that point there? This is going to become negative pi over 4. This is going to become the cosine of negative pi over 4. That's 7 pi over 4. The cosine of that is a positive value. So that's going to be positive radical 2 over 2. So if I go out negative pi over 4 in that direction, then I should go out a positive r of radical 2 over 2, and that does work. Okay, so Okay, so the top half of the leaf is from 0 to pi over 4, but the bottom half of the leaf is from negative pi over 4 to 0. Okay. So what I can do is I can say, well, to find the area using the area formula, we want, okay, alpha to beta, the area is equal to, from alpha to beta, of 1/2 r of theta squared d theta. Okay. So in this case, our r is cosine 2 theta, but our limits of integration have to go from negative pi over 4 to pi over 4. Okay. This is going to be 1/2 times cosine 2 theta squared d theta. Okay, so now let's set this up. Okay, let's do a u substitution on this. U is equal to 2 theta. Du is equal to 2d theta, sorry, 2d theta. So du over 2 is equal to d theta. Okay. If I take u of negative pi over 4, that's negative pi over 2 when I multiply it by 2. And u of pi over 4, that's going to be positive pi over 2. So if we change our limits of integration here to negative pi over 2 to pi over 2, this is going to become 1/2 of cosine of u squared times du over 2. Okay. I'm going to factor out the 1/4 here. The 1/2 times 1/2, that's 1/4. Okay, this is negative pi over 2 and then pi over 2. I get cosine squared u du. Okay. Just make sure I did this correctly. Okay, u is that, pi over 2. Okay, cosine squared u. Yes, okay, that's perfect. Well, yeah, no, it works. Okay, so now what we have to do is we have to change the cosine squared u, okay, using a half angle identity. So let's do that. So this is 1/4 times negative pi over 2, pi over 2 times 1/2 plus 1/2 cosine 2u du. Okay. Okay, so again, I'm going to do another u substitution here. We'll call it a v substitution. V is equal to 2u. dv is equal to 2 du divided by 2. Okay, so we're going to pull out another 1/2 and another 1/2. So this thing's going to have a lot of 1/2s. 1/4. Okay, this is going to be now negative pi to pi, because when I multiply v of pi over 2, I'll get pi, and I'll do a negative. And v of pi over 2 is pi. Okay, v of negative pi over 2 is pi, and v of pi over 2 is pi. So change our limits of integration. This becomes 1/2 plus 1/2 cosine v dv, that's a u, Okay, dv over 2. Okay. Now, I can actually factor a 1/2 here. This becomes 1/2 times 1 plus cosine v. I've got another 1/2 here, and then a dv. So I can pull both of these 1/2s out in front, and this becomes a 1/16 total. Negative pi to pi of 1 plus cosine v dv. Now we can actually integrate. Okay, this is going to be 1 plus, or sorry, v. This is going to be v plus sine v, evaluated from negative pi to pi, of 1 over 16. Okay, so now let's plug in the pi's. Okay, so I've got 1 over 16 times pi plus sine pi minus negative pi plus sine of negative pi. Okay, well, the sine of pi is 0. So that goes to 0, and that goes to 0. Okay, I'm left with pi minus negative pi. That's just pi plus pi, which is 2 pi. And so this becomes pi over 8. Okay. Okay, let's do another one of these. Let's find the area inside an area. Like area. Okay. Yeah. So area inside an area. Let's see what that gives us. Okay, number 2 here. Find the area of the region that lies inside the circle r equals 3 sine theta, and outside the cardioid r equals 1 plus sine theta. Okay, so we've got kind of a little picture to draw here. Okay. So this r equals 3 sine theta, that's going to give me a circle of radius 1.5. It's always kind of half what that number is in front. So along the y-axis, so it will, the diameter is 3, not the radius. Okay, so the diameter is 3. And so it kind of looks like this. Okay, so that's my circle, okay, of diameter 3, radius of 3.5. I'm sorry, 3/2. Okay, 1.5. Okay, that's this guy. The cardioid, okay, will actually go up to 2. Okay, and we drew this one before. Okay, it kind of looked like a heart. Let me try that again. It looks like this, goes up, and then comes up again. Okay, so what do we want? We want this area here. We want the area of the circle, okay, minus the area of the cardioid. Okay, so the area of the circle between the angles where they intersect. We need to figure out where do these two intersect? At what angles? Okay, what is the angle of intersection here? What is this angle? And what is this angle? Because we only wanted to get the areas, okay, between those two angles. So we want the area of the circle minus the area of the cardioid. Okay, since the circle is outside and the cardioid is inside, we want the area between these two. Okay, so we want to find out, well, where's the point of intersection here? Where do they meet? So let's set these equal to each other. Okay, find point of intersection. Find point of intersection, or I should say points of intersection. Okay, we have r equals 3 sine theta. R equals 1 plus sine theta. So we want to know where the r's equal to each other. Well, just set them equal to each other. 3 sine theta equals 1 plus sine theta. Subtract off a sine theta. We get 2 sine theta is equal to 1. Okay, divide by 2, and we want to know where is sine theta equal to 1/2. Okay, where does sine theta equal to 1/2? For theta equal to what? If we look at a unit circle, when is sine 1/2? Well, it's at pi over 6. But it's also equal to 1/2 over here at 5 pi over 6. Okay, so that actually gives me my limits of integration. I know that from pi over 6 to 5 pi over 6, I'm going to integrate. Okay, I want area 1 minus area 2. Okay, the first area is going to be the area of the circle, which is 1/2 3 sine of theta squared d theta minus the integral pi over 6 to 5 pi over 6 of the cardioid, which is 1/2 1 plus sine theta squared d theta. Okay. Let's go ahead and solve these. Okay. So I'm going to pull the 1/2 out in front here. Okay, this is going to be 1/2 times 9. I can actually pull out a 9/2. Well, let's not skip steps. 5 pi over 6. This is 9 sine squared theta d theta. Okay. Minus this guy here, I can multiply this out. This is 1/2 times pi over 6 times 5 pi over 6. Okay, and then this is going to be 1 plus 2 sine theta plus sine squared theta, d theta. Okay, because they have the same number in front and they're going to the same, they're within the same values here for the limits of integration. Since they have the same limits of integration and they're being multiplied by the same value, I can actually put this all under one integral. This will become 1/2 pi over 6, 5 pi over 6. Okay, 9 sine squared theta minus this whole thing of 1 plus 2 sine theta plus sine squared theta d theta. Okay. So 5. So now this becomes 1/2 pi over 6 to 5 pi over 6. Okay, this is going to be 9 sine squared theta minus 1 minus 2 sine theta minus sine squared theta d theta. I combine these two like terms here. It's pi over 6, 5 pi over 6. 8 sine squared theta, okay, minus 2 sine theta minus 1. Okay. Okay, now I'm going to use the double angle formula or half angle formula to change the sine squared theta. So this is going to become 1/2 pi over 6 to 5 pi over 6 of 8 times 1/2 minus 1/2 cosine 2 theta minus 2 sine theta minus 1. Okay. All of that's d theta. Forgot the d theta here. Okay, so distribute the 8. We get 1/2 times 5 pi over 6 times pi over 6. Okay. Okay, this is going to become 4 minus 4 cosine 2 theta minus 2 sine theta minus 1. Okay. Okay, so now combine these here. That's a d theta. We're going to get 1/2 pi over 6 to 5 pi over 6. 4 minus 1 is 3. That's 3 minus 4 cosine 2 theta minus 2 sine theta d theta. We haven't even integrated yet. Okay, this is all just algebra getting it to a place where we can integrate. Okay. Okay. So now I'm going to distribute the 1/2 back. Okay, so this becomes 3/2 integral pi over 6 to 5 pi over 6. 3/2 minus 2 cosine 2 theta minus sine theta d theta. Okay, good times. Okay, now since this has a 2 theta and this has a theta, I'm going to actually break this up into 3 separate integrals. So we're going to go 5 pi over 6 pi over 6 of 3/2 d theta minus 2 times the integral of pi over 6 to 5 pi over 6 cosine 2 theta minus the integral d theta minus the integral pi over 6 to 5 pi over 6 sine theta d theta. Okay, the only one that we really have to worry about is the cosine 2 theta. The rest of them are pretty easy. This is just going to be 3/2 theta evaluated from pi over 6 to 5 pi over 6. This one in the middle, we're going to actually have to do a u sub on. So u is equal to 2 theta, du is equal to 2 d theta divided by 2. And we get du over 2 is equal to d theta. So if I were to change the limits of integration here, this is going to become minus 2. Limits of integration, I have to multiply the limits of integration by 2. So this becomes pi over 3, 5 pi over 3. This is going to become cosine of cosine of u du over 2. But as we can see, what's nice here is the 2 and the du over 2. The 2 under the du, they will cancel out, which is very, very helpful. Okay, the last integral here is just going to be the integral of sine. So this is minus negative cosine of theta, which is just plus cosine, evaluated from pi over 6 to 5 pi over 6. Okay. So now we're just going to integrate this guy here, negative, the negative of the integral of cosine. Well, the integral of cosine is sine. So this becomes sine u from pi over 3 to 5 pi over 3. Okay, this was, again, 3/2 theta from pi over 6 to 5 pi over 6. And this guy was plus cosine theta from pi over 6 to 5 pi over 6. Okay. Now I just have to put in these values. Okay, so this is 3/2 times 5 pi over 6 minus 3/2 times pi over 6. Okay. Minus the sine of 5 pi over 3 minus the sine of pi over 3. Okay. Plus, this is going to be the cosine of 5 pi over 6 minus the cosine of pi over 6. Okay. Okay, so this is 15 over 12 minus 3 over 12, which is going to be 12 over 12. I guess I'll do that. 15 pi over 12 minus 3 pi over 12 is 12 pi over 12, which is pi. Okay. This is going to be a minus plus. So this is minus the sine of 5 pi over 3. Okay. Everybody knows the sine of 5 pi over 3, negative radical 3 over 2, right? We've memorized our unit circle. Okay. Minus the sine of pi over 3, which is a positive radical 3 over 2. Okay. Okay, plus the cosine of 5 pi over 6, that's a positive radical 3 over 2, minus a cosine of pi over 6, or sorry, 5 pi over 6, that's a negative, I'm sorry, my bad, negative radical 3 over 2, because it's in the second quadrant, and then this is minus, okay, radical 3 over 2. Now, if I distribute this negative sign, I get radical 3 over 2 plus radical 3 over 2 plus, or I could say minus radical 3 over 2 minus radical 3 over 2, and everything cancels, cancel, 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 and the answer is pi. Easy, right? Like, no. Okay, well, I mean, it could have been a lot worse. I mean, a lot of things, canceled out, became nice at the very end. But yeah, that's how we do that one. Okay, let's talk about arc length. Okay, arc length. Okay, arc length. Okay, before when we talked about arc length, okay, in we'll call this in rectangular, okay, form, we would have, say, some sort of f of x, okay, that's a y, and yx, our arc length formula would look like this, the square root of 1 plus f prime of x squared dx. I could rewrite that as, this would be from, say, a to b, okay, a to b, of, I could write 1 plus dy dx squared dx. Okay, that's my arc length formula from before when we did arc length of just a function of x. Okay, that's rectangular. Okay, polar form looks like this. So polar form is the following. Okay, sorry, this is L for arc length. Okay, L is equal to the integral from alpha to beta of the square root of r squared plus dr d theta squared. Okay, d theta. Okay. Okay. in parametric form, okay, so for polar form, we have some r of theta, okay, that we do. For rectangular form, we have some f of x. In parametric form, we could have x of t and y of t. However, we could also have x of theta, y of theta. So just because a theta shows up doesn't mean that it's polar. Okay, this is very important. Okay, just because you see a theta doesn't mean that it's in polar form. If you see an x equals something theta and y equals something theta, that's parametric. That's not polar. Okay, if you don't understand that concept, you're going to get a couple of the problems wrong on the exam. Okay, the parameter could be a theta. The parameter could be a t. The parameter could be a z. The parameter could be whatever I want it to be. It could be 1 plus t squared. That could be the parameter. Okay, so just because you see a theta, what you're looking for is it r equals something, or is it x equals something and y equals something? Or is it just y equals something? If it's y equals something, it's rectangular. If it's y equals something in terms of x. If it's x equals something and y equals something, that's parametric. But if it's r equals something in terms of theta, that's polar. Okay, and for parametric form, you're going to want to have this formula. Okay, we'll say the square root of, we'll say this goes from, I don't know, c to d, whatever the parameter is that we would need. Okay, whatever the parameter goes from, say t, or theta goes from, or gamma, or whatever lambda, whatever parameter you're using. Okay, if you have an x in terms of, and y in terms of a third variable, what you're looking for is that third variable. It's x, y, and a third variable. And that third variable could very well be theta. Okay, then we would take dx dt squared plus dy dt squared. Okay, dt. And you integrate with respect to whatever the third variable is. Okay, or what we call the parameter. Okay, so again, a parametric equation can have theta in it. Okay, make a note of that. Okay, write it down in your notes and make a note of it. Say the parameter of parametric equations x of x equals f of theta, y equals g of theta, can have theta as its parameter. Okay, and it does not make it polar. It only makes it polar if r is a function of theta. R must be a function of theta. R is a function of theta. Okay, then it's polar. Right? So we have three different formulas, okay, depending upon what type of function it is. Maybe I'll box these individually. Okay, so we have rectangular, we have polar, and we have parametric. Okay, rectangular, polar, parametric. Okay, so let's do the polar first. Let's do the polar. Notice the extra r in the polar one. That's because we're going around, kind of we're going around a circle. an arc, okay, we end up with this extra r squared, okay? It's very similar to if we had a function, f of x, where this was actually 1 squared, okay? Where it was dx uh, dx over dx, you could think of this as dx over dx squared. Okay, dx over dx squared, boom. Okay, we do end up with an extra r here, r squared. That just becomes 1. Okay, we do end up with an extra r squared here, and that has to deal with the fact that we're taking slices of area. Okay, well, we're taking slices of circumference is really what it is. We're taking a little bit of circumference and a little bit of circumference and a little bit of circumference, and then we're summing it all up. Okay, that circumference. We take a piece of circle, a little tiny piece of circle, and then a little tiny piece of circle, and a little tiny, and we add it all up, and that gives us our arc length in polar form. But we do end up with this extra r squared here. Okay. Note r squared. Okay, note it. Okay, in that formula. Okay. Okay, number 3, example 3. Find the arc length of one cycle of r equals 1 plus sine theta. Okay, so what is 1 plus sine theta? We've seen this guy before. Okay, what is this 1 plus sine theta? What does that make? What shape does that make? Okay, yeah, thank you, Daniel. It's a cardioid. Okay, that's a cardioid. Okay, so we want to know what's the arc length of one cycle of the cardioid. Okay, well, the cardioid theta goes from 0 to 2 pi on a cardioid. The period of a cardioid is 2 pi. Okay. We want to find out, well, what's the arc length here? Okay, what's the total arc length? Okay, of this cardioid. Okay. So we have to find L equaling the integral from 0 to 2 pi of the square root of r squared plus dr d theta, the derivative squared with respect to theta. Okay, so what's dr d theta? We have r is 1 plus sine theta, so dr d theta is just cosine theta. Okay. Okay. So we can plug in now 0 to 2 pi. This is going to be the square root of r squared. Well, that's just 1 plus sine theta squared plus dr d theta, which is cosine theta squared d theta. Right? So this is going to be equal to 0 to 2 pi. I'm going to square this out. 1 plus 2 sine theta plus sine squared theta plus cosine squared theta d theta. Well, the sine squared and the cosine squared, that becomes 1. So that's going to combine with this 1, and so that's just going to be 2. So this is 0 to 2 pi of the square root of 2 plus 2 sine theta d theta. Okay, okay, so at this point it would be I would be like, okay, let's just grab our calculator. Okay, but we can do this you know, you could either grab your calculator at this point and plug that in, and it will give you an exact answer. It should give you an exact answer. Does it give you an exact answer? I think so. Hopefully it does. Let's see if it does. Let's see. Let's do some numerical integration. Number 9 here. Okay, so we want 0 to 2 pi. Okay, of 2 plus 2, I'm going to choose x. Okay, this is going to be the square root. Oops. The square root of 2 plus 2 sine of x. Okay, dx. Okay, does that give me, yes, it gives me 8. Okay, so that, now, if you want to know how you would do this by hand, you can do it by hand. I wouldn't necessarily expect you to know how to do this off the top of your head. What you need to do is you need to multiply by the conjugate. Okay, so in order to solve this, we have to multiply by the conjugate. So we get 2 plus 2 sine theta times the square root of 2 minus 2 sine theta all over the square root of 2 minus 2 sine theta. Okay. So we can do this, it becomes a little messier. Okay, d theta. Let's multiply by the conjugate. Okay. So this becomes 2 squared, which is 4, minus 4 sine squared theta square root all over 2 minus 2 sine theta square root d theta. This is 0 to 2 pi. Okay, the top, okay, this becomes 4 times 1 minus cosine squared theta d theta square root. Okay. Oh, sorry, this is sine again, sorry, sine squared theta. Just thinking ahead to the next step. Okay, and this is 2 minus 2 sine theta on the bottom, square root. Okay, this is 0 to 2 pi. This becomes 1 minus sine 2 theta, which is cosine squared from our Pythagorean identity, 4 times cosine squared theta, square root d theta. Okay. Okay. So then this is the square root of 2, oops, square root of 2 minus 2 sine theta on the bottom, 0 to 2 pi. Okay. Okay, this is going to become 2 times the square root on top times the square root of cosine squared. The square root of cosine squared, when I square something and then take the square root, that actually creates an absolute value. Because if cosine was negative and I square it, it becomes positive. And then I take the square root, it goes back to the original value, but it will always be a positive value. So this is actually equal to 2 times the absolute value of cosine. This is 0 to 2 pi of 2 times the absolute value of cosine theta. Okay, so the output will always have to be positive, okay, for cosine. The output will always have to be positive for cosine. Okay, all over the square root of 2 minus 2 sine theta. Okay, so this guy forces cosine to be positive. Okay, and so in order to get the right answer here, if I look at a unit circle, okay, and I wanted to go, okay, all the way around this circle from 0 to 2 pi. Okay, but I could only let cosines be positive. How would I do that? I could start here. Okay, but then once cosines went negative, I couldn't have this. I can't have this over here. Okay, so because of the symmetry involved, okay, in my functions, what I'm going to do is I'm going to change my limits of integration. But I'm going to do it, I'm going to get twice the area. Okay, so this is going to go 2 times negative pi over 2 to pi over 2. Okay, and then I can get rid of my absolute values. The only way I could get rid of my absolute values is to keep cosine positive. But in order to keep cosine positive, I could only use half the circle, half the unit circle. So I just double it. I double whatever I'm going to get. Okay. For this area. Okay, so now I can do 2 cosine theta. There's a d theta here that I forgot. Okay, all over 2 minus 2 sine theta. Square root d theta. Now I have something that I can use a u sub on. I can do a u substitution on this. So this is going to become 2 cosine, or sorry, let's do a u. U is going to be equal to 2 minus 2 sine theta. Du is equal to 2 cosine theta d theta. Look at that. That's exactly what I got on the top. Okay. So this is going to become 2. Change my limits of integration. If I plug in, well, let's look at my limits of integration real quick. U of negative pi over 2 is going to be equal to 2 minus 2 times the sine of negative pi over 2. Okay, so that's 3 pi over 2, which is sine value is negative 1. So this is 2 plus 2, which is 4. Okay, that's good. What about u of pi over 2? That's 2 minus 2 times the sine of pi over 2. The pi over 2 sine is 1. So this is 2 minus 2, that's 0. Okay, that's cool. So this actually goes from 4 to 0. Don't get that backwards. Okay. It actually goes from 4 to 0. Okay. Of u. Okay. Oh, you know what? I missed the negative sign here. I'm sorry. There should be a negative there for negative 2 cosine u. So it's not a direct substitution. I would get negative over here and a positive. So let's just make sure we get the negative there. So this is going to be negative u to the negative 1/2 power du. Okay, after I do my u substitution. Okay, because the negative went with the du. Okay, because I don't have a negative here for the 2 cosine theta. So let's add 1 to this. Let's do the integration now. This was all to get to so that I can finally integrate. Okay, something very, very simple. Okay, u to the negative 1/2, add 1 to that, I just get 1/2. So this is u to the 1/2. If I divide by 1/2, that's multiplying by 2. So I get negative 2 u to the 1/2. Okay, that's all being multiplied by 2, and then from 4 to 0. Okay. So this is negative 4 u. Sorry, let's just plug in the 0 on 4. Negative 4, 0 to the 1/2 minus negative 4 times 4 to the 1/2. Okay. So 0 to 1/2, that's 0. This whole thing goes to 0. This is negative, negative, which is positive. So that's 4 4 to the 1/2 is the square root of 4. So this becomes 4 times radical 4, which is 4 times 2, which is 8. Okay, and that was what we got on the calculator. Okay. Okay, let's do one last example here. Okay. So okay, we're going to do example 4. Okay, find the arc length of one cycle of the circle defined by, okay, x equals r cosine theta, y equals r sine theta. Okay, where theta is from 0 to 2 pi. Okay, this is just a circle, okay, of radius r. Okay, we're going to treat r as a constant here, not as a variable. Okay, the variable is theta. Okay, r is going to be some general value that I would plug in for r, whatever the radius of the circle is that I'm looking for. Okay, notice that this is not r of theta. Is this parametric or is this polar?
Parametric.
Yeah, it's parametric. This is parametric, not polar. Just because you see r and theta doesn't mean that it's polar. In order for it to be polar, it has to be solved for r. Your function has to be in terms of r, and there has to be no x and y value. Okay, so this is parametric. Okay, so for parametric, L is equal to the square root of dx d theta squared plus dy d theta squared d theta. Okay, integrate from alpha to beta. Okay, so we need to find out, well, what's dx d theta? This is going to become negative r sine theta. Okay, dy d theta is going to be r cosine theta. So L is equal to 0 to 2 pi of the square root of r sine theta squared negative plus r cosine theta squared. Okay, d theta. Okay, this becomes r squared. Okay, times sine squared theta plus r squared cosine squared theta d theta, 0 to 2 pi. And then I'm going to factor out the r squared sine squared theta plus cosine squared theta square root 0 to 2 pi d theta. Okay, this becomes 1. The square root of r squared is what? What's the square root of r squared? What do we just?
R.
It's actually absolute value r. Remember we saw that in the last one. However, okay, we will assume that r is positive, okay, because we're going to say that r is the distance from the origin out to a value, and we're going to let r's be positive, okay? So assume r is positive. Okay, assume positive r. We could let r be negative. It's just going to create a different, I mean, if we let an r be a negative r, it's just going to go in the opposite direction, but it's going to trace the same thing. It's going to give me the same circle. Okay, assume positive r. So we're going to go 0 to 2 pi, okay, of r d theta. Integrate with respect to theta, that's r theta from 0 to 2 pi. Plug in, we get r times 2 pi minus r times 0, which that goes away, and I'm just left with 2 pi r. What is 2 pi r in the world of geometry? What is that?
It's the circumference of a circle.
Yeah, it's the circumference of a circle of radius r, right? So when we said that x was equal to r cosine theta and y is equal to r sine theta, that's just a circle of radius r centered at 0, 0, right? Right? And so wouldn't the arc length of this circle of radius r, wouldn't that arc length of circle radius r, shouldn't that equal the circumference? Yeah. That's the total arc length of that circle. Okay. How do I know that this is a circle centered at r? Well, I could eliminate the parameter here by knowing that a couple of things, knowing that the cosine squared of theta plus the sine squared of theta is equal to 1, right? That's a Pythagorean identity. So I could solve the top one and let cosine of theta equal x over r. I could let sine of theta equal y over r. And so I get x over r squared plus y over r squared is equal to 1. Okay, and so then this becomes x squared over r squared plus y squared over r squared equals 1. Multiply both sides by r squared, and we get x squared plus y squared equals r squared. And what's that the equation of? Circle of radius r centered at 0, 0. Okay, so everything works. Everything it's all good in the hood, as they say. Well, I don't say, but maybe other people say. Anyway, that's it. Okay, peace out.